In this example, we're given a circuit that contains a couple of inductors. This is one here and one here. One is 1 Henry, the other one is 2 Henries. These inductors are not in parallel because they have this 1 ohm connected in between them. So they don't share the same voltage, and since they also do not share the same current because they're not in series, they cannot be combined. That means this circuit is a second order circuit because it contains two energy storage elements, and we should write a differential equation to describe it. So what we were also told is there's a switch in here. So initially these inductors, two inductors and two resistors are not connected to the source, and at time t0 the switch closes and the 5 volts is applied to the rest of the circuit. We were also given some initial conditions. For example, we were told that the initial current flowing through the 2 Henry is actually this one here, which is 6 amps, and that the current flowing through the 1 Henry is actually this one here, which is I1, which is a 2 amp. Okay, and we're being asked to compute whatever is happening with the 1 Henry in here, which is basically the voltage across it and the current flowing through it. That's what we've been asked to compute. All right, so let's get started because we need to figure out how to write this differential equation. And before I get started with that, what I want to do is I want to do the following. I want to write the equation that typically describes how the voltage across an inductor actually relates to the current flowing through it, which is simply V of t is L times d of I of t divided by d of t. Of course, based on passive sign convention, you should write positive or negative. But in both cases in here, because the current is actually flowing to the positive, we should be using the positive. All right, so that means I can rewrite this as VL1, for example, or V1, for example. This is what we called it. V1, which is the one across the 1 Henry in here, and the 2 is the one across the 2 Henry, is simply L, which is 1 Henry, times di1 of t divided by d of t. And similarly, we can say, well, V2 of t is just simply 2 Henries times di of 2 of t divided by d of t. All right, so this is what we have in terms of the voltage and the current across these. So to get started in here, there isn't a single way, but I spent some time on this example and I realized I think it's one of the easiest solutions, or at least that I can think of, is if we write nodal equation at these 2 points and we assume that the reference point in here. So I'll start off with node at 1 in here. I know that this is not an essential node, and I'm writing a nodal equation in here. It's just because it involves some derivatives in here, and will make things a little bit easier. So anyway, let me just do that. So what I will do is I'll write nodal at 1. Okay. So nodal at 1. Well, I have 3 branches in here, and of course we're assuming that this switch has been closed. So what we have is the following. We have that V1 of t, which is the voltage across the 1 Henry, minus 5 divided by 1 ohm plus V1 of t. Actually not V1 of t, because what we care about is actually the current, because nodal is we sum up current leaving, so that's simply I1 of t plus I2 of t, and that should be equal to 0. All right, but we just realized that V1 of t in here is just simply the first derivative of 1 of t, so I'm just going to rewrite it. It's just simpler to just deal with currents at this point, so I get rid of the V1s. So that tells me the I1 of t divided by d of t. This is minus 5 plus I1 of t plus I2 of t equal 0. What I will do is I'll just move the 5 in here, and just that's it. Okay. So this is a first equation in here. So what I'll do is I'll call this 1. So this one here, this equation contains I1 and I2 and the first derivative of I1. And this is I1, I2, and the first derivative of I1. Okay. The next stage is I'm going to write nodal equation right here. Okay. So I don't scroll up and down. What I will do is I will just do this here. I'll just paste an image of it. Okay. All right. So what we're doing is now we assume that this one here is 1, this one here is 2. This is my reference. So I'll write nodal at 2. So nodal at node 2 is just simply V2 of t minus V1 of t divided by 1 ohm plus I2 of t equals 0. Just a couple of currents, and we're going to substitute the values of V1 and V2. Remember, V2 is just simply 2 times the I of 2, the first derivative of I of 2, and V1 is just 1 times the first derivative of I1. So I'll substitute these here, which is 2 times the I2 of t divided by d of t minus, I believe that's di1 of t divided by d of t plus I2 of t equals 0. So I'll call this 2. So now I have a couple of equations, and these equations pretty much contains I1 and I2, I1 and I2, and some derivatives of these I1 and I2. And if you pay a little bit more attention to it, you'll realize that the number 1 in here contains I2 in here alone, and the rest of them are in terms of I1. So if I rearrange the terms a little bit, I might be able to just I will figure out what I2 is in terms of I1. So let me just do that here. So what I can do is I'm going to say from 1, let's do the following. I2 of t is just simply 5 minus I1 of t minus d I1 of t divided by d of t. So now I wrote I2 in terms of I1. So what I will do is I can technically take this one here and substitute it. So I'll be replacing I2 with this part, and this is already in terms of I1. Well, this is the first derivative of I2, so what I can do is I can tell you, well, simply the I2 of t divided by d of t is the derivative. Well, this is 0 minus the I1 of t divided by d of t minus the second derivative of I1 of t, okay, divided by dt squared. So now I can take these two in here and I can substitute, okay, in 2. That's what I can do, which is this one here. So I'll take both of them and I'll just substitute it in here. All right, so what would I end up with? Well, I'll end up with the following. 2 times negative di1 of t divided by d of t minus di1 of t. This is the second derivative, so squared. Okay, minus what I have is this one here, di1 of t divided by d of t plus, well, that will be 5 minus I1 of t minus di1 of t, d of t, and that equals 0. So we do a little bit of algebra, and what we end up with is the following. So I'm going to divide everything by -2 so that I get the highest derivative degree in the positive. So di squared d of t divided by dt squared. And then what do I have? Well, I'll clean it up and come back so that I save you some time. So after doing the algebra, this is what I ended up with. Second derivative of I1t, first derivative of I1t, and then I1t and equals 2.5. It's a second order linear differential equation. We solve it like any other second order differential equation. This tells me, well, this is I1 of t, this is the current flowing through this inductor. This is one of the things I'm looking for, which is I1 of t, which is convenient. So let's do that. So the way we do that is we can say that I1 of t is two solution. It's the particular solution and the complementary solution. We have a particular solution because this is 2.5, not 0. Well, we know that the particular solution is the following. Well, the particular solution for a constant forcing function is just simply constant. So that means 0 plus 0 plus 0.5 I1 particular t. I'm just going to call it I particular just for the sake of consistency here. I can just call it P1, C1. This is P1 in here, and that should equal 2.5. That means the particular solution is just simply 2.5 divided by 2, which is just simply 5 amps. So that's basically the particular solution. I'll just highlight it in here. Okay, good. So now what's next? Well, next is we need to find the complementary solution. So the complementary solution, IC of t, is based on the equation, which is the following. It's the second derivative of I1, okay, plus 2, the first derivative of I1 divided by dt plus 0.5 I1 of t equal, this time it's 0. This is the homogeneous equation. So that means the characteristic equation is s squared plus 2s plus 0.5 equals 0. That means 2 alpha equals 2. That means alpha is simply 1. Well, omega 0 squared is just 0.5. That means omega squared is just simply the square root of 0.5. And that number is 0.707. And both of them are basically rads per second, and this is rads per second. Of course, what we can do is we can say alpha is greater than omega 0, which is good. That means, well, good or not, that means that this is overdamped. Okay, so overdamped, that means there's no oscillation, there's no cosines or sines. Of course, that means we need to figure out what S1 and S2 is. We know that simply S1 is, well, you can solve it by knowing the equation, by knowing the rules, or you can just tell me the discriminant delta is just simply b squared minus 4 times 1 times 0.5, and that equals to equal, well, I think that here should be 2, not 4, because b is 2. Like 2 squared is 4. So that's 4 minus 2, which is simply 2. That means the square root of the discriminant is just simply square root of 2, which is 1.41. Right, that tells me that the first root, S1, is just simply negative alpha, which is negative 1, negative or plus 1.41 divided by 2, and that should be equal to S2 is similar to negative 1, negative 1.41 divided by 2, and that should be equal to, well, let me just find the solutions. I believe this will be 0.29 in the negative, this will be negative 171, okay? And frankly speaking, this is also, it's not alpha 2, this one here is 2. That's how it should be. So it's negative 2 because I'm basically saying negative b plus the square root of delta divided by 2a, and negative b minus square root of delta divided by 2, and those are the solution. The final answers are correct. Well, the final answers for the roots, that is. All right. So that means the particular solution I1, or complementary solution, sorry, IC1 of t is simply k1 e to the negative 0.29 of t plus k2 e to the negative 1.71 of t. All right, now what we need to do is we need to find the complete solution. The complete solution, I1 of t, is just simply, I believe, what was the particular solution is 5 plus k1 e to the negative 0.29 of t plus k2 e to the negative 171 of t. What we need to do right now is just to figure out what these constant k1 and k2 are equal to using initial conditions. Just as a quick reminder, this is how the circuit looked like. So we have some initial conditions. For example, I can tell you I1 at 0 is just simply 2 amps. This is actually given to us here. Okay. That means we can just simply say, well, 2 is 5 plus k1 plus k2. I just substituted t equals 0 in here, t equals 0. So this is 1, this is 1. So that's the first equation. Actually, we can do a little algebra and we get k1 plus k2 equals negative 3. Okay, here. Now for the second initial condition, what we can have is the following. What we need is actually di1, let me just write it here, di1 of t divided by d of t. Well, we know that this is, well, we know that L times di1 of t divided by a of t is just simply v1 of t. And this is L1, which in our case is just simply 1 Henry. So that's what we have, which basically is that. Okay, so what we can tell is the following. V1 of t, do I know V1 of t? I don't know V1 of t, at least not readily. I'm looking for V1 of t, but what I'm interested in is figuring out the following. di1 of t divided by d of t at t equals 0 is simply V1 evaluated at 0. And what we need to do is we need to figure out that initial condition for V1 equals 0. What's happening right after we switch? Well, what we do know is the following. We know the current in here, okay? And we know the current in here. And that's all that we know. So technically we can figure out what the current flowing in here so we can know the voltage drop across this. And we know the voltage drop across this because the current after T0 doesn't. So let's compute it. So what I will do is I'll tell you the following here. So right after switching, that here is closed. So this is T equals 0 plus. What we do know is the following, that the current in here right before switching, right after switching, is simply 6 amps. We also know that the current flowing through here, actually we don't know the current flowing through here, but we know the current through here is 2 amps. Well, if this is 6, this is 2, that means this is for sure an 8 amps. So we technically know that the current flowing through the 1 amp, 1 ohm resistor, this 1 ohm resistance is 8. And I think now we can more or less write some sort of a KVL or KCL equation. So for example, we can write a KVL equation in here and we figure out what that V1 of t, the 0 V1 of t. So let me just do that. I will do this here. Okay, I'll write a KVL equation. This KVL equation will be negative 5 plus 8 times 1 plus V1 evaluated at 0 equals 0. Remember again, this is only for initial condition because that 8 is only initial because this has been 2, this has been 6, exactly at t equals 0. And that basically tells me that the V1 of 0, the initial voltage, is simply 5 minus 8, which is negative 3. And that's basically volt. All right, so now we can substitute this here by negative 3. So now we know this is negative 3. we can continue from there. So negative 3 volts, okay, this is of course V1 0 plus, this is 0 1 plus in here, and that's plus. Okay, because remember, the voltage across an inductor can be difference between 0 minus and 0 plus. It just happened, we just computed it to 0 plus now. Okay, all right, so where are we? Well, what we need to do right now is just basically go back to this equation, take the first derivative, set it to 0, and then equate it to negative 3. That's what we can do, and that's exactly what I'm about to do right now. So I'm going to tell you the I1 of t divided by d of t is simply, well, 0 plus k1 times negative 0.29 e to the negative 0.29 of t plus k2 times negative 1.71 e to the negative 1.7, I think that's not 1 here, that's just 1.7, okay, and that's here is t. Okay, actually it's 7.1, 7.1, let me just do that here, 7.1, because I think this here is 7.1, yeah, this is, so I just have to write 7.1 in here. Alright, so we got that. Good. So what's left? What's left is the following. We're gonna do this here as well at t equals 0. That means this here is at 0. That means the whole thing here is 1. Okay, this one here is also 1. So that gives me the following. So negative 3 equals negative 0.29 k1, negative 1.71 k2, and that's pretty much, well, we can get rid of the negatives in here, make this into a positive, and what we have is we have the second equation. So two equations, two unknowns, those are k1, k2, k1, k2. By solving them, we'll figure out the values of these constants. So the values for these constants are the following. That is k1 is negative 5.73, and k2 is simply 2.73. So the solution for I1 of t for that circuit that we've been looking at is 5 minus 5.73 e to the negative 0.29 of t. That's coming from here. See those? I'm just writing these, I'm just substituting k1 and k2. Okay, let me just do that here so that I can see it. Plus k2, which is 2.73 e to the negative 1.71 of t. And that here is amps for t is greater than or equal to 0. So we were able to figure out the current flowing through that inductor in here. So let me just do that. We were able to figure out what I1 of t is here, and the question is also asking us to figure out V1 of t. But based on the rule, what we have is the following. V1 of t is simply L times d I1 of t divided by d of t, but our L in this particular case is 1 Henry, so all you have to do is just take the derivative. And that's simply V1 of t is just negative, well, that becomes negative 5.73 multiplied by negative 0.29. Of course, the derivative of 5 is 0. I just didn't say it. E to the negative 0.29 of t plus what we have is the following 2.73 times negative 1.71 e to the negative 1.71 of t. And once you do the algebra, what you'll end up with is 166 e to the negative 0.29 of t, negative 4.67 e to the negative 171 of t. That's V1 of t, and that's voltage, that's volts for t is greater than 0. So just to highlight the answers, so the answers are the following. This is I of t, okay, and this is the V of t in here. We can figure out the V2 and I2 as well if we wanted to. But anyway, a little bit of plots so that we can get these answers in here. That's what we have. So what we've seen is in the following, and we can double check. I didn't do some sanity check very quickly. So let's assume, well, we know the initial current here is 2. If this is 0, that means this E is 1, this E is 1. Hopefully, if you calculate it, which I did, 5 minus 5.73, it will be negative 0.73 plus 2.73 is 2. So the initial current is good. And the final current is, this will be 0, this will be 0, which should be 5. And if you think about it, the final current, the inductor is actually just simply a wire. And when it's a wire, everything here is just basically shorted out. Nothing happens. Basically nothing happened in here. And I have a 1 ohm. That simply tells me that the current flowing through it is 5 divided by 1, which is 5 amps. So it's good. So that's good. I'm assuming the voltage is similar. So voltage initially, you can substitute this to be 0, this to be 0, and hopefully you get the negative 3. Yeah, approximately you get negative 3. And then at infinity, in both cases, we get 0 because that's a wire. The voltage across it will be 0, which is good. And we can see it in here. That's the following. So what we did say is the current starts at 2 because this is the initial, and it's trying to basically reach the final value of 5, and that's the final value of 5. There's no oscillation whatsoever, so it's at 2, it goes down, and so forth. It might appear it's oscillating, it's just not. It's just because it's exchanging the energies between the two different inductors and the source in here. Similarly with the voltage, we started with a -3 as an initial, and then the final one is 1, or 0, sorry, and it goes up in here and just reaches it after a short period of time.